Okay, good morning, everybody. Welcome to the Thursday plenary. Just got the usual reminders for you that we have a code of conduct to be mindful when interacting with others. The lost and found is the registration desk, and to keep an eye on those social batteries and use our quiet room if you have to or want to. Our virtual participants should be muted when they're not speaking. No, we cannot turn off the doorbell. We will not leave that box checked next year, don't worry, but we will hear the doorbell as whenever the computer at the podium is sharing sound. And another reminder all day, all participants in all breakout rooms to speak into the microphone so that our virtual participants can hear us. There's the picture that Emily took yesterday. Another wonderful picture. It turned out great. So I think we'll get that circulated so that you can grab it and have a copy. I don't know. Ask Emily for it. Yeah. Let's see how it turned out. And the date for next year, we can now share it with you. So 2026 Rubin Community Workshop, save the date in your calendar, July 27th to 31st, and we'll be back at Slack in Menlo Park. Okay, that's all the announcements I have. So I'm going to welcome two members of the Science Organizing Committee to the stage to tell you about what you're going to hear today.
Good morning, everyone. Welcome to the Rubin Research Spotlights Plenary. My name is Shreya Anand, and I am an LSST DA Catalyst postdoctoral fellow.
And my name is Siegfried Ecke. I'm a faculty at UAUC and with the Solar System Science Collaboration. So today we have 4 speakers, excellent, all of them. And we are really happy to start you out with
Yaoyuan Mao. So it's my pleasure to introduce Yaoyuan Mao, an assistant professor of physics and astronomy at the University of Utah, and our first speaker in the Rubin Research Spotlights Plenary. Yao was born and raised in Taipei, Taiwan, and received their PhD in physics from Stanford University in 2016. Yao studies low-mass galaxies and their connection to dark matter using astronomical surveys and numerical simulations. For more than a decade, Yao has been involved in the Rubin community and specifically in DESC. Yao currently serves as a co-convener of the Science Release and Validation Working Group in DESC and has previously co-led the Dark Matter working group. Yao was awarded the builder status by DESC in 2019. Yao is the current maintainer of the Astronomy and Astrophysics Outlist. Please join me in welcoming Yao today to be our first speaker.
Hi, everyone. Hopefully you can all see my slide and hear me. To be honest, I won't be able to know if you are responding to me. So I'm going to assume, since no one is stopping me, that everything is working and starting.
Yes, we can see your slides. Yes.
Thank you. So this is a somewhat impossible talk to give with the amount of time and the things I want to talk about. So I was just starting by saying that, as you hear from the introduction, and thank you so much for that, I started low-mass galaxy and particularly the connection with dark matter. So here is a map that where you're looking at the colored points are the map of a local universe. So this is a light cone, go all the way onto 100 megaparsec. And all the color points are one of the low-mass galaxies. And by low-mass galaxy, I defined it as like stellar mass less than 10^9 solar masses. And the main takeaway from this plot is that, well, actually on this plot, you can see some gray points. It's probably very difficult to see if you are, distant from the screen. But there are a few gray points, and the gray points are not low-mass galaxies, they're high-mass galaxies. And so the main point is that actually, if you map out a local universe, most of the galaxy that you should be able to see, that map out a large-scale structure, will be low-mass galaxy. They dominate the population especially in the local universe. Well, I mean, it's in all universe, but just that in the local universe, we can see them. But they are, even within very nearby distance, they're very difficult to find because they're faint and very difficult to identify them. But you can also see from this plot that you really need that in order to map out the large scale structure. And so one of the very exciting things that I'm looking forward using Rubin is that it will allow us to map out the low mass galaxy in the local universe with a wide range of techniques, and actually extend some of the existing techniques to a much further distance. So when you're looking here, lower two bars here, they're showing you the technique that are applicable at the different distance ranges. And with Rubin and a few upcoming space surveys, we will be able to push each of this method to a further distance and allow us to find more low mass galaxy using this wide range techniques. And we have been already making progress even before Rubin turned on. We now are able to find some of this partially resolved galaxy out to like 1 to 2 megaparsec. Even with precursor surveys, and Rubin will allow us to do that to all the way to like 10-ish megaparsec, which is really amazing. And also we will have a lot more informative photometry that allow us to get a distance estimate using photometry only to all the way to maybe almost 100 megaparsec. So here is what I meant by photometric information. So here is something that we did with precursor survey. This is work led by, a series of work led by John Wood at Space Telescope and Elise Darrell-Ford then at Stanford, looking at, using photometric information only, so using the images only to select low mass galaxy candidate, and I should say low mass, low redshift galaxy candidate, but they are in a way interchangeable because you can only see the low mass galaxy. They are at very low redshift. And you can see that this different tier means how likely we think they are a low mass, low redshift galaxy, tier 1 being the most likely. And you can see that after we get the spectra, we can indeed find many of this very low redshift galaxy. And you can see the redshift distribution of the tier 1, tier 2, tier 3. This is a follow-up using DESI. Yeah, I should say that this plot makes it less impressive because this is in log scale, but really, the tier 1 sample are much, much lower redshift compared to the other 2 tier in terms of where the population peaks. So finding these things will allow us to map out the dark matter structure. We can find kind of where the lowest mass dark matter halo might be. We can see where the transition region is from halos that host galaxy to halos that don't host galaxy. But beyond dark matter science, it also allows us to study the black hole AGN in those low mass galaxy, understanding galaxy evolution, studying very, very local cosmology. And many of these low mass galaxy will become hosts of supernovae and other transients as we go to Fenter and Fenter region in the time domain science. So I'm going to highlight one more result from like precursor survey is that by using this kind of photometric selection of low mass galaxy, we were actually able to do gravitational lensing by stacking the signal from the halos around this very nearby low mass galaxy. So here is actually the recent work that by a student, Joseph Turton, and their advisor Alex Amon, doing weak lensing using the DS sources and the photometric selection that I mentioned earlier to measure basically the halo mass of the stacked low mass galaxy. And you are looking at left is the lensing signal that we measured for 3 different stellar mass spins. And then on the right, you're looking at after we put it into the stellar mass halo mass relation, they're roughly like here. They are not too far away. They are very, the noise is still big, but they are pretty similar to what you can refer from previous studies. And I think this is the very first work to being able, excuse me, to extend the low mass galaxy measurement to extend the weak lensing measurement to this low mass stellar mass. And so just imagine what you can do with Rubin once you are able to find these low mass galaxies. Now, there's a lot of challenges because we need to be able to identify them. We only have photometric data, so there's a lot of work to do. But I'm very excited that and hopeful that we'll be able to do that. So in the past few years, I've been working with a group of people trying to argue that Rubin Observatory can really act as a flagship dark matter experiment. And we have a serious white paper, including what kind of science you can do with Rubin. And then we submit Astro 2020 white paper, Snowmass 2021 white paper. And then in the end, from the 2022 P5 report, we finally got a secondary driver for Rubin on the dark matter side. But this is important. I think one of the reasons that this is needed, that we need to argue, is that to do some of this science with dark matter science with Rubin, you really require a community of people to come together. And we highlight this in one of our white paper and said that establishing the VRC Rubin observatory as the flagship dark matter experiment will bring the dark matter community together to make critical discoveries. So it's not just about, like, you might ask, like, you could do all of these things that I talk about, like, you know, we have Rubin data, we have data for you already. You can start to go into look for resolved low mass galaxies, etc. But it is important to bring the community together to tackle some of this very, very difficult work with the sheer amount of data that we're going to have. And so with that, it's almost impossible for me to not address some of the recent things that's happening in Rubin and how that affects the community as a whole. I think most of people in the room probably are familiar with what happened, but if you don't, there was a New York Times article I linked here. There was one sentence saying here regarding some specific thing happened about archiving LGBTQ channels. This one sentence was much heavier if you live through that period of time. If you're interested, here is how you can find out what happened. You can go to the general channel on the Discovery Analysis Slack, click one of the dates, any date will be fine. You can jump to a specific date, and then you can choose January 31st, 2025. And then you can start to read from there. I should say it's a very heavy read. If you want to do that, make sure you find the place that you can take care of yourself if you want to do that. I'm also a maintainer of the astronomy and astrophysics outlets. I can tell you that in the last 6 months, I have received more requests from people to remove their names from the outlets than I have ever received since I started becoming a maintainer in 2018. Most of the requests come from people at NORAD, Space Telescope, NASA, and other federal agencies. And it's just heartbreaking to get those emails, take people's name off, and then send them a message saying that I'm sorry. And I'm going to stop sharing my screen here and use my last minute to say a few words. First of all, for all the LGBTQ people in the audience, you're not alone, and you should do whatever that is best for you. You are not required to hide yourself, but you're also not required to fight. You should be yourself. You should be celebrated. This is not right. And I hope you find the peace and can take care of yourself. For everyone else, I have two messages. One is that we all have our own circles of influence, and we need to make decisions in various ways as we, do our work. But one significant difference when you are making decisions and you are not the group of people being impacted is that we sometimes forget about how to actually make the balance. Like for me, deciding whether I can talk 3 more minutes about exciting science versus talking about what I'm talking about right now is a choice that both choices harm me in some ways. In one, I lose the chance to highlight more about exciting science I can talk about. And the other, I have to, forego something that really I care deeply about, and it's something that deeply personally about myself. But when you are in a position that you're making these different decisions for others, you are not really facing this kind of dilemma. And that is something that I want you to remember. I can tell you that in the past 6 months, I got a lot of people want to talk to me, learning what we have experienced. But a lot of the time, the conversation turned out to be like, I need to make sure that they are okay. Like, I need to say that you're doing as much as you can already. And that, I think, is the biggest difference. Like, sorry, this is hard, but you need to live with the harm that your decision, regardless whether you have control or not, that has resulted. Because that is the only way that you can balance in the future when you have to make those difficult decisions. If we come to you and say, everything's okay, don't worry about it, then you're never able to learn to do that balance. And so I hope that everyone, regardless your position and rules, because you need to make decisions in this landscape, learn what are the consequences of those decisions and actually live them, not just learn about them. Like you need to be in the position that understand how the consequences impact others as if they're impacting you. And that is the only way as we move forward as a community that we can really find the balance in this very challenging landscape. So I will stop here and thank you for your time.
Thank you so much, Yao. Thank you so much, Yao. I think we have time for one quick question. Yes, please.
Hi, Yao, this is Bob. I just wanted to thank you for your courage to speak today, for what you have shared with this group. And I want to acknowledge that, Yao and I talked multiple times after the events earlier this year took place, and I didn't get most of it right. But what I want to acknowledge is Yao's honesty in helping me understand what my actions mean and taking ownership of them. I'm not trying to claim anything's resolved. I'm not trying to claim that I specifically have done something that's going to make a difference for Yao, but I do want to sincerely thank him for his honesty in how he communicated with me during that time. Thanks.
Thanks again, Yao. Thank you very much for speaking. The next speaker in the plenary is Igor Andrioni. Igor is an assistant professor at the University of North Carolina, Chapel Hill. Igor hails from Italy and received his PhD from the Swinburne Institute of Technology in Melbourne, Australia. His research interests include multi-messenger astrophysics, high-energy transients, tidal disruption events, fast transients, and many more. Igor is the current co-chair of the Transient and Variable Stars collaboration, as well as the chair of the Rubin Users Committee. He co-led the Rubin TOO 2024 workshop report, which provided official recommendations for the current Rubin TOO program, Target of Opportunity program. Igor has also co-led mentorship trainings for the broader Rubin community and serves as a mentor himself for the LSST DA Catalyst Fellowship. Please join me in giving Igor a warm welcome. Oh, sorry.
Thank you, Shreya. And thank you all, especially those that help us become more aware of who we are as a community, help us become better individual, a better community. Thank you for all the actions. And let me echo that you're not alone. Not all of us are ready to face some challenges, but with communication and empathy and action, hopefully we'll get somewhere. So never be afraid, standing for what you believe in. And starting from there, let me dig in a bit in the science that is the closest to my heart, and how I think realizing this science is a community effort, in fact. So my name is Igor Andreoni. I will talk about transients, multi-messenger sources. I would like to start by giving my more personal perspective on how we got all the way to the target of opportunity program, that I will also refer to as TOO program. And in the final bit, I will talk about how, with my closest circle, we have played around with DP1, made discoveries, and some takeaways. Why do we even care about multi-messenger astronomy? Linking electromagnetic radiation with gravitational waves in particular, or neutrinos, cosmic rays. Well, for gravitational wave multi-messenger astronomy, we can answer so many deep questions. For example, why does the universe look like it does, even in our neighborhood? Why does gold even exist? It really shouldn't exist, or at least not in the abundance that we witness. But it's not just that. Thanks to the study of multi-messenger sources, we can get direct insight on the physics of relativistic sources. We can go all the way, peek into the equation of state of neutron stars and compact objects. This is key to do cosmology in new ways, understanding what's going on with the tension between the nearby and distant universe observations. However, it's a challenging job. There are the LIGO Virgo detectors that find gravitational wave signal, tell us more or less where they are in the sky. That truly helps. But also, something we have been trying to do for quite a few years now is trying to find these sources associated to these multi-messenger events in surveys, like Rubin, like during LSST, or in preparation for LSST using ZTF and other wide field cameras. It's challenging because if you look at the plot on the left, these transient counterparts that we expect to find in the optical are pretty faint, fainter than supernovae, peaking at -14 to -16 magnitudes. And they fade away so quickly. Typical fade rate in most bands in the order of 1 magnitude per day. This does not make it an easy job. So back in 2018-19, it was still okay to propose for very wild survey strategy for LSST. So the one we propose is every day observing G and I band. This may be the best way for us to find kilonovae. And then as time progresses, all the OPSIM infrastructure was created, perfection made available. So thank you very much to Lean, Peter, everyone worked so hard to make that happen. And that allowed many of us in the community to do realistic injections of this type of transients, try to recover them, and start from even more informed models to make realistic predictions. However, like I mentioned before, the multi-messenger aspect truly is key to take the research we can do to the next level. As you can tell from the plot at the top left here, when a gravitational wave signal arrives, we may expect, if we're lucky enough in the orientation of the system, a gamma ray signal to accompany it. And if we're good, and we have an instrument like Rubin available to do TOO observations, we may be lucky enough to pinpoint precisely the location of the event, thanks to the discovery of these kilonovae, these optical and infrared transients. So that's why many of us have started thinking long and hard, how can we do a good job with Rubin by designing effective strategies for the follow-up of gravitational waves? So like, as you can see in this Gantt chart, we started taking in consideration different scenarios, in particular related to the areas, the size of the areas that we have to image in order to cover a good probability percentage in order to catch the right location of the gravitational wave signal where it was generated. And depending on how broad the area of the sky to search are, you may employ different strategies. So there was a first very unifying community effort led by Ralph Margutti in 2018 in the form of a white paper. And that blossomed a few years later, last year in 2024, in a workshop in which the community from all science collaboration came together to really make a practical recommendation on the Target of Opportunity program. And something I loved last night, putting together these two figures. The difference is the one on the left is a simulation. This is how we envision a possible follow-up of gravitational wave source. You can see the map in the darker colors, and the circles are the projected observations with Rubin. And on the right is the plot that Sean McBride provided me with yesterday, 5 minutes before the yesterday plenary, with perfect timing. And you can see how well the two match. And this has been an incredible milestone. So a big shout out to Sean, to the Rubin project, but also to the community that has come together to push for this program to even happen and then provide guidance on how to do it more and more effectively as we move forward. In the last 3-4 minutes, we switch to the second part, DP1. So you have June 30, data release. So what do you do from that day on? You do a hackathon, especially if you're lucky enough to be surrounded by some new postdoc and students who are very excited to dig in the Rubin data. And in fact, our playing around resulted in what I think is the first collection of reported transients that were newly identified in Rubin observatory data. It's something even just saying that gives me the goosebumps. It's happening. It's reality. It's reported. And now let's do science with it. In particular, students John and Sarah focus on the search for possible tidal disruption events in the data set. Obviously, we knew the chances are so little because these are rare events and the area of DP1 is limited. We're looking for stars that are shredded by the gravity of massive black holes at the center of galaxies. And John is doing incredible work with the Zwicky Transient Facility and the SOAR telescope to do spectroscopic studies of the earliest phases of these events. So hopefully we will hear more about these applications in Rubin as more data become available. We also found a number of already reported transients that were present in Rubin data. Postdoc Akash Anumar Lapudi, he's a radio and gamma ray astronomer, very interesting combination. So he thought, why don't we exploit radio surveys and try to find cross matches, see what's there in DP1. And some curious cases came out. And that gave him the idea of now conducting a study on synergies between existing and future radio surveys and Rubin based on real data from DP1. And Jim Freeburn, who's here somewhere in the audience, then focused on the discovery of new extragalactic transients, started off from almost 400,000 DIA objects, and we boiled it down to 11 realistically astrophysical extragalactic transients. You can see here on the left an image from archival sources taken with the dark energy camera, and to the right, this bright blue spot is a young supernova that was discovered with Rubin. Here is a glimpse to some of the light curves of these newly identified objects. They, for being the first data products revealed, they're really good. We can definitely start doing the science. And in particular, we used code developed at Harvard in collaboration with Kailis DeSoto in particular to do photometric classification. So using light curves to try to understand what is what. And then we compare the detections that we have with expectations from the literature. We fall a bit short, but that's totally expected, especially because in most cases, the transience was present in the template, and that limits our ability to make discovery. But we're very close. That tells us that the pipelines are doing really well. And the paper has been posted on arXiv and appeared last night. So I encourage all of you to go check it out. And before concluding, I will also point out that another paper came out last night that we coordinated publication with, led by Easy Dong, on image subtraction between LSST images and DECAM to discover transients. And I will leave you with a few takeaways. I will just highlight one. For the target of opportunity program, we need practice, practice, practice. We need testing on simulation, but possibly with real events. We have to keep learning, keep doing better, we're using the great momentum we have now. And kind of the question I have is, how can we help as a community? As a field, we're known to use a strong word, cutthroat. But when it comes to Rubin, we really came together on multiple occasions. Let us help whenever possible, whenever you think is good. And thank you for listening to me today.
Thank you very much, Igor. It was great. We have time for one quick question, and just a quick reminder, if you have questions, please post them on the Slack channel because they're going to be there. The speakers can come and follow up with you online. Okay, thank you. Is there one question in the room, perhaps? Do we have a question online? Okay, then thank you so much, Igor. Really appreciate that. You have a chance to be followed up on later. It is my greatest pleasure to welcome our next speaker, Anja van der Linden. Anja is an associate professor in the Department of Physics and Astronomy at Stony Brook. Her primary research interests relate to galaxy clusters, ranging from clusters as cosmological probes to gravitational lensing and galaxy evolution in clusters. She's the Deputy Technical Coordinator of the LSST Dark Energy Science Collaboration, or DESC, where she previously served as the co-convener of the Clusters Working Group and on the Collaboration Council as well. So she is now also serving as the Rubin user on the Rubin user committee. So thank you very much, Anja. Please. Quickly try to.
Right. Thank you very much for that kind introduction and for giving me the opportunity to talk about some of our work. We'll talk about a first weak lensing measurement by Rubin around this galaxy cluster, ABLE 360. This is work that was done primarily within the commissioning team, but also within the LSST DESC collaboration. And I'm really standing here on behalf of many people that contributed to this work, and in particular, many early career scientists. I included a lot of pictures and names on my slides. If you see any of them, please go and talk to them. This is super exciting work. All right, a brief recap of gravitational lensing, in particular weak lensing. Well, matter deflects light. And so if we place a massive object in between some background galaxies and our telescope, sorry, this is the wrong telescope. But anyway, we see a distorted image of these background galaxies, in addition to, in this case, the cluster galaxies. In this cartoon on the left, we're going to take a slightly closer look at that. Imagine for a moment that all the galaxies were spherical and they're round. We put a cluster in front, and that changes the shapes of the galaxies in the background. If the cluster is very massive, then the galaxy that is right behind the center of it will be strongly lensed. This is when we see multiple images and giant arcs. They make very pretty pictures. If we go further away, these galaxies are not multiply imaged. However, they are still distorted in a way that aligns them tangentially to the direction to the cluster center. If all the galaxies were round, you can immediately see this weak lensing signal here. But that's not the case. Galaxies intrinsically have all kinds of shapes, so we'll just call them elliptical, even though some of them are spirals. And so the picture at the bottom is more closer to the truth. In this case, you can still see the strong lensing, But now if you look at a single galaxy, you cannot see how much it was distorted. Statistically, however, in the picture on the left, the average orientation will be 0, cancels out. In the picture on the right, if you just take the colorful galaxies, you can measure an average tangential alignment. There are 3 flavors of weak lensing that we distinguish. Cluster weak lensing is kind of what I just showed you. Here, the distortion of the order of a few %. And so if you have good data and a massive cluster, you can measure this on a single cluster. If you instead want to study the dark matter halos of galaxies, then the effect by single galaxy is way too small to measure individually, but we can do a stacked measurement and still measure distortion that is less than 1%. Or if we just ignore all the lenses and we just measure the distortions of the background galaxies, statistically, we can still get a statistical measurement of the properties of the dark matter filaments that are causing the lensing. And this is called cosmic shear. Quite often people will call this weak lensing, but really there's these 3 flavors of weak lensing. Given that cluster weak lensing is the strongest form of weak lensing, it's not a surprise that cluster weak lensing was in fact the first measurement of weak lensing by none other than Tony Tyson back in 1990. And so in this measurement, he basically counted how many galaxies are tangentially aligned, and he saw that the blue galaxies, which we expect to see in the background, are more often tangentially aligned rather than being at a 45-degree angle or round in other shapes. And this measurement was part of the motivation for Tony and others to propose the dark matter telescope, which has now become the LSST and then the Rubin Observatory. Dark matter telescope because gravitational lensing allows us to see the properties of dark matter. All right, so I said I'm going to talk about commissioning data, so data taken with a ComCam camera. All right, part of the motivation here is that these clusters are actually quite useful to test the data relatively early on. We have these large elliptical galaxies, so we care about sky subtraction. This is an overdense extragalactic field by definition, so deblending is important. We have all of these red sequence galaxies, so we can infer things about photometry and photometric redshifts. But also, if there's a massive cluster, and this telescope is built to do weak lensing, we expect it to see a tangential shear signal from the cluster. And so a number of members of the LSST DES clusters working group joined the in-kind commissioning team in order to perform these tests. And we are distributed over, I think actually most of the science teams, not quite all. I'm giving 2 talks at this conference. Yesterday, I mainly talked about the galaxy stuff. Today, I will talk about the lensing stuff, but I included some of the bonus slides if you want to see more about the galaxy tests. All right, if you're saying, wait a minute, there's no cluster in DP1, there's no cluster field, it's hiding in the asteroid field, okay? So the asteroid field, the boundary conditions for observing that was to pick a field that is close to the ecliptic and within some right ascension range. Thankfully, the DSV team decided to center this field on the most massive cluster in the ACT catalog. And so within this field, right at the center, there's this relatively unknown cluster A with 316. The data was taken in a 2x2 mosaic. And so we actually have to divide the number of exposures by 4 to get the depth at a given point. This data is relatively shallow. It's less than 1 year depth. The seeing is not great for weak lensing, but we'll make do with what we have. So can we measure a cluster weak lensing signal? Right, there's some other complications in this field, and that is that there's a fair amount of galactic extinction. So we mask that out. In the future for weak lensing, we're going to stick to the dark blue area. If we did that here, we lose a lot of the area, so we only cut the red parts here. There's stars, we mask out the stars. And there's also galactic cirrus, and that part we had to hand mask. Then we need to select the galaxies that are actually in the background. Galaxies in the cluster and in front of it are not being lensed by the cluster. And we can first identify what are the cluster galaxies. And so you see this really nice red sequence sticking out in the color magnitude diagrams. We remove all of these objects from the lensing catalog because we expect them to be in the cluster. This, by the way, is also the only field with DESI overlap. And people have calculated photometric redshifts from this data and can compare them to the DESI spectroscopy in this field. And things are looking pretty good, even with just GRIZ photometry. Right, and then we come to the actual weak lensing measurement, which is a measurement of the shapes of the galaxies in this field. Weak lensing is really difficult. You need really good data for that. And part of why it's difficult is that we're looking for a change in the galaxy shape from this shape to over here. This is very exaggerated. The actual change is usually much smaller. However, these galaxies are all very far away, so they're very small on the sky, which means that they pass through the atmosphere and the telescope, they become blurry. The light ends up on a finite number of pixels, and there's noise. And so in the end, all we have are many of these galaxies. This one's actually pretty high signal to noise. And based on this, we want to infer what the change is from this shape to that shape. Part of the issue here is that the shape is actually of the order of how elliptical the point spread function can be. And one of the critical steps in weak lensing is that you can measure and model the point spread function very accurately. So one of the first things we had to do is actually look at how well the current PSF models perform. This is a visualization of the PSF over this field. So for every star, we draw a little line that says how elliptical that star is. But over here is the residuals between the measured PSF and the model. And so you see the residuals are very small, and there's no correlated structure in the residuals here. So that looks good. So then we can go and try weak lensing measurement. The DP1 catalog does include weak lensing shapes from the shape HSM catalog. And if we plot up the tangential alignment, these are the blue points here, we actually see a signal that is in excellent agreement with what we expect, given a Z-based mass estimate of the cluster. So these are the blue points. We have a detection. And the cross shear, this is when we look at 45-degree angles, is consistent with 0. This is another excellent test of how well things are doing. We didn't stop there. We tried 2 other shape estimators, which DESC will want to use in the future. And in particular, MetaDetect is the one that's also being planned for DP2. And we also see the cluster there. Very good. All right. Well, last month now, we can also do science with this as part of the DESC collaboration. For DESC cluster cosmology, we're going to turn these profiles of tangential shear into mass estimates. So DESC has been preparing for that. So we now have 3 shear measurements and 8 photo Zs, and we're fitting 3 different kinds of profiles. Anyway, first mass estimates look pretty good, consistent with the SE estimates. We can also look at the shear ratio using the photo Zs. Given our cosmology, we have an expectation of how the shear should increase as a function of redshift behind the cluster. There's a limited number of galaxies here, right? So the error bars are very large, but there's no red flags, which means photo Zs and shear estimates look pretty good. We can also use the weak lensing measurement to make a map of where the matter is in this field. We find a 6 sigma detection of a matter peak in the center of the field. If we do this with a cross shear, they're very small. Good job. No systematics. We can also do some science about this cluster. And we see that in all the measurements that we apply to it, the matter distribution is very elongated. This starts with the BCG, east-west oriented. The red sequence galaxies have the same orientation. We even see them weak lensing, which is pretty awesome, as well as in the X-ray gas and in the SE. This is a 1 megaparsec circle. If we zoom out, we can start to imagine we're seeing filaments extending here in both the red sequence galaxies and the lensing. We have empirical evidence that Ruben can do weak lensing. Congratulations. This was not trivial. This was a challenging field for weak lensing. It's relatively shallow. The seeing is greater than arcsecond. The PSF is elliptical. There's high extinction. These asteroids are awesome, but for us, they're a bit of a nuisance. And yet the lensing is looking really good. And so I think this gives credit not just to the instrument, but also that the science pipelines are performing very, very well. So big thank you for everybody who is making that happen. I also want to point out that most of the work here was done by in-kind commissioners. We documented this work in TechNotes, currently finalizing the science part and writing the paper. And in particular, many early career scientists worked on this. And so they have learned a lot about clusters and weak lensing, but they also learned a lot about Ruben and Ruben data and how to work with that. And I think that is a great thing to take from this project. In particular, also the TechNotes are a way to give the junior people, their first author publication. So I think all of this actually worked really well. Thank you very much.
Thank you so much, Anya. This was great. We have time for one quick question. If there is one. Yes, there is one here over there.
Hi, Anya. Yeah, great talk. I have one question regarding this. You've done this analysis with 3 share estimators, right? And there seems to be some scatter between them, which was kind of perhaps slightly bigger than expected, but also like Anakal in some sense even had like somewhat bigger error bars, like as if it was noisier, which goes in the opposite direction I expected. Can you comment on that?
Yeah, so that's something we're looking into. However, the only thing to keep in mind that these 3 plots are not necessarily the same object. Every one of these methods does its own detection, does its own photometry, does its own source selection. Actually, I think specifically here, for shape HSM and MetaDetect, they're rejecting galaxies that are in the red sequence on all 3 of these plots, but this is not yet the case for the Anacal one. And so that has fewer objects in the catalog itself.
Thank you again. Let's thank Anya again for the great talk. Our next speaker hardly requires an introduction. I need to understand how PowerPoint works, though. So I'm also very happy to welcome Professor Mario Juric. Professor Juric is from the University of Washington. He is the Director Emeritus of the Dirac Institute, which probably just means that he's going to be doing he leads Ruben Observatory's effort to discover any kind of solar system objects and interstellar interlopers, and his work focuses using big data. And of course, he wants to explore the solar system, but also the Milky Way. Thank you so much, Mario. Please.
Thank you, Siegfried. Okay. So, on the 23rd morning of sweet July's grace, the world rubbed its eyes. Ruben lit up the place. With cameras and notepads and press badges flashing, the DC elite were all pimped up and dashing. There's science, they cried. What a beautiful feat, as telescope galaxies danced on the screen neat. With neckties and lanyards and strong coffee brews, they toasted the cosmos and posed for the news. But far to the west, while the big show began, in Washington state, there unfurled a great plan. No suits, no balloons, no canopy trade, just researchers hunched and submissions made.
Submitting the first Rubin discoveries to the Minor Planet Center.
All right, here we go. Queuing for submission. Submitting the queue.
Still uploading.
I have no idea how long this should take.
Well, 2 minutes in.
Do you have an email by chance?
All right, let me take a look.
While DC partied and toasted the host, 2 huskies were annoyed. Why won't these this thing post? No time for retreat. The team depends on us. They hunted down bugs without glamour or fuss.
Its first Rubin asteroid discoveries rolling into the Minor Planet Center.
So with MPC emails and faint screens aglow, they launched little pebbles the whole world would know. And that's how Rubin got its first data released. All right, now let's, now that you've all woken up, let's talk about the first look asteroid data set. So what I what I showed you there was Joachim Moens, one of our team members, and I waking up at 5 a.m. in the morning on the date of the Rubin first look in order to submit about 300,000 observations, so about 2,000 new asteroids, so that we can actually say that we discovered these things a couple of hours later. These are the reports. This is the report, the actual file. It was compiled by Ari Hines, who's here over here, his code, and Jake Kurlander, one of our students, who built these pipelines. 2,103 reported discoveries, 343,000 reported observations. This data set that Rubin released is quite large, and it's quite diverse. It encompasses nearly all dynamical classes in the Milky Way, sorry, in the solar system. It shows we're able to find objects throughout the solar system. We applied a very conservative cut to that first submission to get it out. And so more and more, there are more TNOs that we have that haven't yet been accepted. But this gives you a sense for what's out there. All of these asteroids are located in the M49 Virgo field. Here you see them on the right-hand side. Note how there's this greater density on the east as asteroids float into the field, so we find more and more of them as they come in. This is a beautiful image that we showed at first look. It's even more beautiful once you upload it to astrometry.net and solve for WCS. Thank you, Dustin and company. Because then that allows you to do things like this. You can actually take all those asteroids from the Minor Planet Center and plot them where they are. There are numerous observations for each object. On the right here is a histogram of the number of observations per object in the RFL submission. The object with fewest observation has 16 of them, with maximum is about 500, and the median number of observation is 132. The cadence is such that we observed over about 2 weeks, and there are 9 nights total in submission. So this already gives you a sense that this is going to be a really interesting data set for studying variability, studying light curves. And that is the case. So here is a plot of photometry, of photometric repeatability as a function of magnitude. We got G band, R band, and I band, and what you see in this gray solid curve is the theoretical floor we would expect to see from just photon noise. And what you see above that are the asteroids in blue. And the interesting thing about them is that they essentially hug that line. They come quite close to it, which means that those asteroids that don't vary are well measured. And all these data are available. So there's about 340,000 observations. They're available at the Minor Planet Center or any of the sites that mirror the MPC database, or there's a really convenient CSV file that were exported by friends at the B612 Asteroid Institute and shared on the Solar System Science Collaboration channel less than 24 hours after we submitted all of this. So there's a link up there, ls.st/dat. I promise I did not ask for that link. It was auto-generated, but /dat is perfect. That's where you go for the data. All right, now, where there's data, there's science. And here's a team that got together right after the release to go and try to take a look at some of those light curves. Jelko, this gift will follow you till the end of your life. So the photometry I showed you a slide ago, one of the things that you might notice is, yes, there are many of these objects that are close to this line. Ask me about the dip at the end. But there are also many objects up here in this region. And that means that they're variable. And indeed, let's pick one of these objects. And if you zoom in, you're going to see a light curve. If you zoom in on the top is the light curve across many days. And on the bottom is when you zoom in to just one night. And you can beautifully see, well, first of all, that asteroids are indeed variable. Second, that they have colors. These different colored points are from different filters, and note how the parts are offset from one another. You can basically measure asteroid colors by just looking at this plot. And the other thing is that with the Rubin RFL data set, this was that easy to notice. It's just a wonderful data set of time domain studies. Also, look at the magnitude in the y-axis. This is something that I've noticed in previous talks as well. We all kind of don't notice anymore, but that's 24th magnitude down there. And you can infer the error bar from just the noise in the light curve. There's almost none. This is a wonderful data set. So then what do you do next? You take these light curves and you phase them. And here's an example of one object, 2025 MM82, nice phase light curve, 1.1 spin period. This asteroid moves or spins quite rapidly. This is not the only asteroid. There's more of them. And as has become fashion with these kind of images, there's even more. These are just 24 of about 75 asteroids that for which this team established the limits. And I'm going to reveal something that those of you who haven't been at Sarah's presentation yesterday don't know yet. Sarah Greenstreet and her team here have discovered a class of objects that rotates extremely quickly. These objects here, if you look at down the bottom, the previous one that I showed you spins roughly once every hour. That's already very fast for an asteroid. These guys spin in 1.88 minutes and 3.78 minutes. We've never seen something like that, especially not in the asteroid belt, in the main belt. This is my blatant attempt of extracting another minute or two from the chairs, because one of the chairs helped create this figure. But it shows you that you have to start answering some serious questions about what these asteroids are in terms of how they hold themselves together, how they not fall apart. All of these Rubin discoveries are way up in this plot, showing they have to have reasonable tensile strength. And I'm going to stop here because this is really Sarah Greenstreet's talk and work. Sarah and her students have built all of this over the last couple of weeks. Come to the 1:30 solar system session to go to see the details. But wait, there's more. So just as we were starting to work on this paper, that was going to be the thing to do, this thing showed up. The third ever interstellar object was discovered on July 1st by the Atlas survey, our friends in Hawaii. And we got the idea to take a look and see if we had it in our data, and we did. However, there were problems. One of the things that we cannot do is release data until 30 days after they were taken due to something called the commissioning embargo. However, one does not simply ignore such an opportunity. And we haven't. So the leadership at all levels, Rubin, agencies, and science collaborations rapidly worked together to develop a solution. This here is an artist's depictions of one of our meetings. It was exactly like this. And we came up with a solution. Pixel data remained with the project, but the work on analysis was opened. We spooled up an ad hoc collaboration with over 150 solar system science collaboration members, did the analysis and wrote the paper in 3 days, working around the world, and literally the clock. This is really an amazing example of an excellent collaboration that resulted in this paper. It provided the earliest high-resolution images of the new interstellar comet. It demonstrated that the object was already active at that time. The paper is now in archive and submitted to AppJL, and really, really a huge thank you to everyone who made this happen, and kudos to Colin, Pedro, Devanshi, and everyone else on this paper, and especially to Meg Schwalm, the lead of the Solar System Science Collaboration, who really, really guided this group of 150 plus people to producing a paper that doesn't look like a salad. Thanks, Meg. So come again 1:30 in Solar Systems session to see more in Colin's talk. So I'll end with just a couple of slides looking ahead. This is what a typical night in LSST will look like. This is 400,000 observations. This is what the first year of LSST is going to look like. In essentially a couple of weeks, we discover hundreds of thousands of new objects, and over the first year, we're going to double the number of known asteroids. This is an increase that's unprecedented. This is where the numbers are going to go towards the end of the survey. And we've already started this. This here is this SV survey, the Science Validation Survey. It already covers, over the last 5 weeks, we already covered roughly a third of the solar system, a third of the ecliptic. This is by far the largest outer solar system survey ever conducted. We expect hundreds of thousands of new asteroids, thousands of neutrinos, many comets, maybe even a planet. So an amazing data set already collected. Let's find a way to get it out. So I'll kind of end on this note. Our knowledge of the solar system is about to expand dramatically, and this data set really has the potential to transform how we view the solar system. But as we think about what to do next and how to start the LSST, I want to show you, I wanted to just bring attention to all the talks in this session. With the little data that we put out, we're already starting to do excellent science. So as we think whether we should add a little bit more to commissioning or maybe delay the data release to make the data release even better and so on, just keep in mind that what we already have is phenomenal. Let's get it out there. Let's get the science done. And so to end, so here's to the folks, both on stage and off-site, who wrangle the data and make sure it's right. For while flash bulbs may pop and champagne may spray, it's grit, code, and coffee that wins Rubin's Day. So let's give a big round of applause to all the folks who made this possible. Thank you.
So much, Mario, for a very creative introduction and conclusion, and for a fantastic talk. So unfortunately, we don't have time for questions right now, but it is the coffee break. So please feel free to ask questions, approach each of the speakers and ask them anything or have a discussion with them. Thank you so much for attending this plenary session, and have a great coffee break.